Hello and welcome to the second lecture of week 8 of the course Introduction to Generativity. Although this lecture and the forthcoming 2 or 3 lectures are located in the Mathematical Preliminaries-II of the course, I would like to draw your attention to the fact that you will see a gradual influx of physics ideas and gravitation-related physical phenomena in these lectures. The critical importance of this lecture and the forthcoming 2 or 3 lectures cannot be overemphasized. The level of success of your understanding of generativity in this course will be essentially determined by the grasp of your material presented in this lecture and the forthcoming 2 or 3 lectures. With that preamble, let me go to the references. As I had mentioned in the previous lecture, I'm not going to give references for individual lectures for this part of the course, which is dedicated to Riemannian geometry. Instead, I'm going to cite some general references with the for this entire part. So the page numbers and section numbers are indicated here, which I have stated in the previous lecture. The lecture notes for this particular lecture will be posted from the NPTEL-NOC website as usual. And finally, those who are looking for a little bit more mathematical depth detail can look at Barrett O'Neill's Semi-Riemannian geometry with applications to generativity. As for background, I'm going to assume some familiarity with the idea of general Fourier transformations in the context of manifolds, that is, familiarity with the idea of inner charge transition functions or diffeomorphisms, as well as people should know the transformation rules for tensors. I also expect some familiarity with the concept of a Riemannian manifold and the associated properties of the Riemannian metric. For example, raising and lowering operations. Finally, I'm going to also appeal to the knowledge of Lie derivatives and integral curves of smooth vector fields and the idea of Lie bracket of 2 vectors. All right, let's look at the agenda for today's lecture. Our aim is to become familiar with the some physics facts such as point particle moving in curved spacetime, which will lead us to the very important geodesic equation. Then we'll discuss symmetries of metric and the associated Killing vectors, and we will see that will result in some constants of motion or integrals of motion, as we like to say, and these integrals of motion are critical in solving the geodesic equation. Finally, we will look at the notion of local inertial frames, or sometimes these are also called geodesic coordinates in the literature. Okay, let's start with the motion of a point particle on a Riemannian manifold. So, if we consider a Riemannian manifold M comma G, then a point particle moving on this manifold will trace out a one-dimensional curve, which is given by x mu of lambda. The coordinates of the points on the curve are functions of this variable lambda, which takes values on the real line. So this one-dimensional curve, which is traced out by a particle moving on the manifold, is called the whirl line. Most of you are familiar with this idea from special relativity. Now, given the whirl line, one can always define a general coordinate invariant length of the whirl line, which is given by integral over the infinitesimal length of the whirl line. So if this is the whirl line between 2 close by points, which are separated by coordinates x and x plus dx, the distance between these 2 points, as we learned from the last lecture, is given by square root of dx squared, where dx squared is given in terms of the metric and the infinitesimal change in the coordinates. And if you integrate that infinitesimal distance between the points 1 and 2, you get the total length of the whirl line between the points 1 and 2. Now, remember, x is not an arbitrary point, it must lie on the whirl line, so that's why I've indicated this functional dependence on lambda. So g mu is a function of x, which in turn is a function of lambda. And then dx mu, this infinitesimal increment or difference in the coordinate, because the coordinates are functions of lambda, must be given by this rule, dx d lambda times d lambda, d lambda. So there'll be a d lambda for this guy, and there'll be a d lambda for this guy, which is a square quantity, and then comes out of the square root. And instead here, inside the square root, you have the derivatives. Okay? So this is how it looks if the parameterization of the curve or the whirl line is given to you. Now, as it turns out in relativity, this interval can be positive, negative, or zero. In particular, we know for particles, point particles, which are moving with speed less than the speed of light, this must be negative. So this much we know from special relativity itself. Okay, so for point particles which are moving with the speed less than the speed of light, that is for subluminal motion, one has a time-like curve. Okay, a time-like curve because ds square is less negative everywhere. In that case, instead of the proper length, we can define the proper time t, which is given by integral of this quantity square root of minus dx square, because ds square is negative, minus, we put this extra minus sign so that it becomes positive definite. And then we can rewrite this using parameterization. X is a function of lambda, diminutive of x. Again, x is a function of lambda, and then this becomes this integral over lambda. So this defines the proper time, okay, for a particle which is moving with the speed less than the speed of light. Now it turns out that the action for a point particle or massive point particle is given in terms of the whirl line proper time. So as you can see, the action is equal to minus m times t. This is just equal to t. Let me not write the integral because we have defined already the integral to be t. So the action is minus mt, and you can see that when we do not have a gravitational field, that is g mu becomes equal to eta mu, this reduces to the point particle action in special relativity. So please recall that at the end of the Fierce-Pauli segment of the course, what you understood is that as a result of the gravitational field, in particular the Fierce-Pauli field h mu, the Minkowski metric got distorted to some other metric, general curve metric g mu, which is given by eta mu plus h mu to first order. And of course, as you go on adding higher order corrections, you have a series in h mu. Okay, so in order to get to this, starting from the reverse direction, if you start from a gravitational field, if you turn off the gravitational field, you should get special relativity. So here we can see that if we turn this g mu into the flat metric, which you can do if you have no gravitational field, then this action reduces to the corresponding action in special relativity. I'm sorry, there's a typo here. One should have minus m here. I missed that. Sorry about that. So this action has certain features which I want to draw your attention to. First of all, as you can see, all the indices are contracted, right? All the indices mu nu are contracted. So it's a general coordinate invariant action. And also the fact that if you change your parameterization of the curve to some other parameterization, lambda prime, which is function of lambda, f of lambda, or the monotonic function of lambda, let's say, then this action is invariant because the Jacobian of transformation of lambda will cancel out with the two factors of f which come from the denominator in this lambdas in the denominator. And one can show that if we change the parameterization from lambda to lambda prime, all that happens is that these lambdas get converted into lambda prime. That's all. The form of the action doesn't change. So this symmetry or this freedom of being able to change the parameterization of the curve anytime is sometimes called reparameterization symmetry. And this is a crucial fact about this point particle action. It has two symmetries. First is that it is of course general coordinate invariant because it only depends on the proper time. And secondly, it has this reparameterization symmetry. All right. So we have this point particle action. And of course, we can get the equation of motion. We can get the equation of motion by either extremizing the action, or we can directly write down the Euler-Lagrange equation with the Lagrangian, which is given by this. Now, please note that I'm introducing some new symbols here, notation here. Instead of dx d lambda, I'm using x dot, which is the same as derivative with respect to lambda. Okay? So I'm using this abbreviated notation, which is a bit more compact and reduces clutter of notation. Now, if you vary the action, or if you write down directly the Euler-Lagrange equation of motion, it looks something like this, which is not very illuminating. All we can see is there are a bunch of square roots, and one side has velocities, and both sides have velocities, so on and so forth. So this is, although this is the equation of motion, this is not the most illuminating form, and you can gain some intuition by recasting it in some in a way which makes it look a bit simpler. So this is the form. This can be rearranged in the form in the blue fonts here. So this is a bit more familiar. You have acceleration, like second order derivative of x, and you have certain terms which are quadratic in velocities, and a term which has linear in velocities, which for some reason the term which is linear in velocities I've written on the right hand side. And you can see two undefined symbols here, kappa and this weird curly brackets mu nu rho. I'll come to them one by one. First, this kappa of lambda is actually the derivative of lambda derivative of the quantity log of square root of x dot square. Remember, x dot square is nothing but this quantity. So this is x dot square root of minus x dot square is this quantity. Take a log of that and take a derivative with respect to lambda. That is what kappa is. Now, what is this quantity, which has a weird looking curly brackets, no alphabet, but indices, mu as a subscript, nu and rho, and a superscript mu. So these are the so-called Christoffel symbols. Now they're defined to be quantities which depend on the derivative, first derivative of the metric, and the metric inverse metric. Technically speaking, some people would say these are Christoffel symbols of the second kind, but I'm not going to observe the distinction. I'm just going to say this is Christoffel symbols. And as the name suggests, we introduced this in the last lecture, that the word symbol is reserved for indexed objects which do not transform like components of a tensor. Okay? So this Christoffel symbols is not a tensor. If you look at the transformation property of this, when I change coordinates, this will not transform like components of a 1, 2 tensor. Now, although this looks, this form of this point particle trajectory which I wrote down is simpler than the previous form, it is, one can still find a parameterization in the form in which the form will simplify further, and that can be done by exercising our freedom of a choice of parameterization. Now, we can choose a parameterization in which this kappa vanishes. And that parameterization, those parameters for which kappa vanishes are called affine parameters. And what we have is the equation of motion, which is called the geodesic equation, as you can see, in affine parameterization, in which the right hand side is 0. Okay? So the equation consists of two terms. One is the acceleration term, because it has second order derivative of x mu with respect to the affine parameter. And the second term, which consists of velocities, and the right hand side vanishes. So whenever the right hand side vanishes, or the kappa vanishes, we call that parameterization, that special choice of lambda, an affine parameterization. And one can show that this lambda is actually related to the proper time, tau. Remember, proper time is defined to be, d tau, this is not tau. D of tau, infinitesimal proper time, is defined by the infinitesimal length, or not the length, interval, square root of the interval squared. So if you choose this proportional to the affine parameter, then you get a simplification of the geodesic equation. Geodesic equation in general parameterization is non-homogeneous, right hand side is non-zero, and you get this homogeneous form whenever you choose lambda to be AT or for A tau plus B, where A and B are arbitrary real constants. Okay, so that's why most of the time we choose proper time to be the right parameter, because then the geodesic equation looks simpler. Since we extremize the time, one can think of geodesics as shortest time curves. Okay, or although we derive this under the condition that there is subluminal motion, and let me go back to the action, and we extremize the proper time, one can also try to extremize this, which then it will not represent trajectories of point particles, but still they will represent some kind of extremization of the length, minimization of the length, and they will still give you curves of shortest length if you take them to be space-like, curves of shortest distance, and that equation will again look like the geodesic equation, except lambda will not be the proper time anymore. This lambda will be the proper distance, proper length or proper distance. Okay, ds squared. So now I'm going with the positive sign because ds squared is positive. Okay. Finally, I should mention that this equation also holds for massless particles, like for example photons, or so even for massless particles, you might say that this action is not valid, because for massless particles we know m is 0, so this action is not well defined. However, one can show using an alternative action that even for massless particles such as photons, you get the same equation of motion, which is this. Or you can take a general equation of motion, which will turn out to be this. And in the case of photons, as you know, one cannot define rest frame, so there is no proper time or proper length for that matter. So then this affine parameter is whatever that makes, whatever parameterization that makes the right, and that's all. We then try to solve it. Now, of course, how do we solve it? This is not an easy equation to solve. As you can see, it's a second order nonlinear equation, so it presents us a considerable challenge while solving it. But if the metric has certain symmetries, then we can gain some advantage. This is the next topic of discussion: symmetries of the metric, or isometries. So what are isometries? Let me first define them. Isometries are defined to be special general coordinate transformations or diffeomorphisms for which the metric form remains unchanged. For example, we know if we are in Minkowski space, then Lorentz transformations are isometries, because under Lorentz transformation, the metric does not change. Minkowski metric does not change, right? So one can ask the question for general spacetime, which is not Minkowski, the general Riemannian manifold. What are the isometries of the metric? That means, what is the general coordinate transformation which leave the form of the metric unchanged? What do we mean by that? Let me start first with the passive point of view. Here what we do is go from one coordinate frame to the other, from x to x prime. So it's the same point, but we're talking about two different coordinate charts which are covering the same point. And in one chart, in the left chart, this has coordinate x, and on the second chart, it has, and x prime is a smooth function of x, and vice versa. So we have this. Now, since the metric is a rank 0, 2 tensor, we know how the metric tensor components will change when I go from this coordinate system to that coordinate system. And in the, so left the second coordinate system, which is the prime coordinate system, in which we have the metric that is given in terms of the metric in the unprimed coordinate system by this formula. Most of you know this. You can see, because it's a 0, 2 rank tensor, two factors of the inverse Jacobian matrix appearing here. Now, this is true for a general case of a general coordinate transformation. Now, in order for this to be an isometry, one must have the form of the metric must be the same as before. Okay, G prime nu of x prime is same as G nu of x prime. So the form of the metric, of course, the coordinate of the point has changed, but the form of the metric has not changed. Okay, the same function. Now, this equation, we can simplify this further by looking at continuous general coordinate transformations. What are continuous transformations? Well, continuous transformations are those which contain a parameter which I can dial from 0 to some finite value. For example, one can consider translation or rotation. In the rotation, there is a parameter called the angle, which I can dial from 0 to some finite value. Or when I do a translation, there is a parameter called the translation parameter, the shift parameter, which can be dialed from 0 to a finite value. So whenever a general coordinate transformation is labeled or contains dependence on a continuous parameter which can be dialed from 0 to some finite value, we will call that a continuous general coordinate transformation. Again, I gave a couple of examples. Rotation, in which the angle determines by how much you perform a transformation, or the translation, in which the shift parameter will determine how much you translate by. These are examples of continuous GCTs. Now, whenever we have continuous transformations, because the transformation depends on a real parameter, which we are dialing from 0, I can do an expansion amount in the parameter. Right? When the parameter is 0, we have no transformation. When the parameter is dialed away from 0, then we get some finite transformation. So let me present the infinitesimal form. So epsilon is the parameter, and by epsilon, we denote it by epsilon because we mean a very small transformation. Then this transformation will look something like this. X prime will be equal to x minus epsilon times some function of x, which is k, plus second order terms, so on and so forth, higher order terms. So this epsilon is the parameter which controls the general coordinate transformation. So this parameter we keep infinitesimal, then we restrict ourselves to the first order or infinitesimal form. Then this vector k, which appears as the coefficient of epsilon, is called a generator of the transformation. Okay, generator of the GCT. I should have made it in bold fonts because it's a significant concept. If we plug this infinitesimal form, if we are looking at an infinitesimal symmetry or infinitesimal isometry, then we can plug this form in these, and of course x prime here as well. If we do that for an isometry, we get a constraint on k, which is called the killing vector. That is the killing vector equation. Okay, so these generators of isometries are called isometry generators are called killing vectors, and the killing vectors obey a specific equation which follows from this equation, these two equations, which is called the killing vector equation. I've written it here at the bottom in purple fonts. So in principle, given a metric G mu, these components, you can solve for this equation to determine the case. So in principle, given a metric, one can always solve this equation to find out what are the isometries of the metric. As I said, isometries of the metric are those general coordinate transformations which you perform, and as the result of which is that the form of the metric does not. All right, so one can approach this concept of isometry from the active point of view as well, that is using diffeomorphisms. So in the active point of view, you start with the point which is coordinate x on the manifold, and you map it to a point x prime. So this is diffeomorphism, which means the map is invertible and it is smooth in both directions. Okay, both the map and the inverse map are smooth as well. So we take a diffeomorphism, and then we can define an infinitesimal diffeomorphism in which this point x prime is separated from x by a small amount in terms of coordinates, which is parameterized by this continuous parameter epsilon times k. Okay, I can always, so in other words, as you can see from this equation, if you remember a little bit of the things which we learned before, x and x prime lie on the integral curve of k. So this way of writing should make it clear. When we learn about integral curves, we know the integral curve has a generator, which is the vector field, and 2 points in the integral curve generated by the vector field k is given by this form. So we have diffeomorphism, which is a result of a flow along the integral curve generated by k, and the way we define isometry in this language is that the pullback metric along the integral curve generator, that is the vector field K, is the same as the metric itself. Okay, so under this, the metric, which I would denote by F star G, the pullback metric is same as the metric field itself at that point. Okay, so that just means that the lead derivative of the metric must vanish. Lead derivative of the metric with respect to the vector field K must vanish, right? So as we know, if the pullback is equal to the metric itself, the lead derivative should vanish. So this is the condition. And if you remember what is the killing vector of 0, 2 form field, 0, 2 field, tensor field, then you'll see that it gives us back the same killing equation. All right. So either way, either the passive or the active, you get the killing equation. The killing equation in the active form is written much more compactly. So I like it more because it has a very compact appearance. There's another alternative form of the killing vector equation which you will see while reading papers or the literature. And this is in terms of covariant derivatives, which I'm not going to introduce in this lecture, but it is for the next lecture. In terms of covariant derivative, the killing vector equation appears very nice, aesthetically pleasing, as you can see. It's this covariant derivative, mu derivative of the k nu component plus the other way, plus the reverse order is equal. All right, so as I promised that the reason we are interested in looking at the symmetries of the metric, because at the end of the day we want to solve this geodesic equation. So how does the metric having symmetries help us? Well, this is because if the metric has symmetries, that is, if it has killing vectors, then one can have conserved charges. So this is the velocity, 4 velocity, as you can see, dot product of the 4 velocity with the killing vector. So it's x dot 4 vector dot product with k. Okay, this I have written in component index notation, and this is index-free notation. So this quantity I'm claiming to be a conserved quantity along geodesics, along the trajectory. And I will leave it as a homework. It's very easy to show that if you take the tau derivative of both sides of this equation, and then use the geodesic equation for this part, and if you use the killing vector equation for this part, this gives you the conservation law. Okay, the proof is left as a homework. I think you should be able to do these elementary proofs. As I said, all you need to do is use the geodesic equation for this part when the time derivative acts on this part, and when the time derivative acts on that part, on the k mu part, you should use the killing vector equation to simplify it, and you should see everything cancels out, and you get 0. All right, so this is the critical significance of symmetries of the metric, is that because they admit, they result in conserved charges. This is exactly what Noether's theorem is about. If you have symmetries or continuous symmetries, then there exists conserved charges. Here I've written the significance of this existence of charges. One can have this equation, which is the conservation law, and this is the first order in x mu. Okay, first order derivative, ordinary differential equation, and many times this can be readily integrated rather than the geodesic equation, which is a second order equation. On the other hand, the conservation law, which we will get, are first order, and they can be readily integrated. So in fact, all the geodesics we will learn in this course, in Schwarzschild or other geometries, will admit conserved charges, and this will be our preferred method to solve the geodesic equation. We will, one way of proving geometry is through geodesics. That means we have to solve the geodesic equation, and all the cases we will study, all the geometries we will look at, we will use this method of conserved charges to solve for geodesics. We will look for a first integral of motion or a conserved charge that will give us a first order equation, which we will try to integrate and get the trajectory or the geodesic. Now, I'll end this slide with a comment that, so if you look at this chart, this is first order in velocities. Okay, this is linear in velocities, but it is in principle possible to have charges which are higher order in velocities. Okay, higher order charges. These will exist provided the geometry has not killing vectors but killing tensors. Killing tensors are symmetric tensors. So for example, I have a rank n killing tensors which has index alpha 1 to alpha n, and it is symmetric under the swap of all these indices. Okay, it's symmetric under the swap of any and all of these n indices. So these are killing tensors if they satisfy this property that the symmetrized covariant derivative of this vanishes. As you can guess, this is a simple generalization of the killing vector equation written in covariant derivatives, except the killing vector has only one index. When we go to killing tensors, we have sorry about that, n indices, and then the symmetrized covariant derivative of that vanishes. If that vanishes, then this geometry will admit a conserved charge, which would be nth order in the velocity. Okay, you have n factors of the velocity appearing here, contracted with the k. So this is possible. I'm not going to talk about this in detail. Maybe in some later lectures we can talk about this. But this is just a comment. Okay, so it seems like symmetries and the existence of killing vectors is critical in solving for the geodesics. Then one has to ask the question, well, how do I get the killing vectors in the first place? And the answer, one of the answers is that, well, you apply some direct method, that is solve the KB, the killing vector equation, and you directly determine all the killing vectors for the geometry. However, there is a faster and more efficient method, which is simple inspection. Take a look at the metric components, Gimenu, and if you find that the Gimenus are independent of some coordinate, let's say x alpha is missing from the Gimenus, it is not a function of the Gimenus. Gimenus are not a function of the x alpha. Then one can conclude that k is del alpha, k equals del alpha. So remember, del alpha is a basis and its component is 1. So that's why I didn't write it here. This is the component and the basis. This is a vector. This is a killing vector. Okay. You can check that this will satisfy the killing vector equation, which is kind of obvious. Let me just go back to the killing vector equation to show why this is very obvious. As you can see here, these two terms will vanish because the component is 1 and the derivative of a constant is 0. So these two terms vanish. And the third component will also go to 0. The third term will also go to 0 because this component is non-vanishing when you have the coordinate alpha, but the metric components are independent of the coordinate alpha. So the derivative of the metric component with respect to the alpha coordinate is also 0. So all three terms vanish, and we have the killing vector equation trivially satisfied. Hence, this is one rule that by simple inspection, look at the metric components. If the metric components do not have dependence on some particular coordinate, let's say x alpha, then del alpha is definitely a killing vector. That is one way. And I'll give a couple of examples. Let's consider the Euclidean plane in 2 dimensions, which is given by the line element dx squared plus dy squared. So the metric components are 1, 1, and there is no xy term. So the xy term metric component 1, 2 is 0. So this comes with 0. So the metric components are 1, 1, 0. So the metric components do not depend on either x or y. Okay, the metric components do not depend on x or y. They are both constants. All three of them are constants. 1, 1, 0. So then, by this rule which I mentioned, del x and del y, these will be killing vectors. I've denoted them by capital X and capital Y. These are 2 killing vectors. One can check indeed that is true. As I said, this is obviously true. Another second example which I will cite is the 2-sphere S2, which is given by this metric in coordinates which can be identified as the colatitude and the longitude phi, the colatitude theta and the longitude phi. And looking at the metric components, you can see the metric components are 1 sine square theta, and for the d theta d phi term, it is 0. So none of these metric components, 1 sine square theta and 0, contain any dependence on phi, the longitude. Hence, f, which is given by del of phi, is going to be a killing vector. Okay, so one can easily check that because none of the metric components depend. All three of them, they do not depend on phi. Del phi is going to be a killing vector. Okay. Another fact is that if x and y are two killing vectors, then the Lie bracket of x and y is also going to be a killing vector. Now, this term is fact can be explained heuristically a little bit. So this rule can be justified heuristically. Consider the integral curve generated by x and y. So this is the integral curve generated by x, and this is the integral curve generated by y at some point. And let's say we draw another integral curve of y here, and from this point, another integral curve of x here. Okay. So as I said in the lecture on Lie brackets, that if the Lie bracket of x and y doesn't vanish, this parallelogram doesn't close, and there's a gap between these 2 points, which is given by this segment, and this segment is proportional to x commutator y, not x commutator, I mean Lie bracket of x and y. So if I remember the definition of symmetry, is that if I go along integral curve generated by the symmetry by the killing vector, the metric form will not change. So if I start from here, if I traverse down the integral curve of y, the metric form will not change. If I further traverse down the integral curve of x, the metric form will not change because x is also a killing vector. Further again, y, it will not change. And finally, a final leg is also another integral curve along x, generated by x. So the metric will not, form of the metric will not change either. But taking this strip, the metric doesn't change, so I can imagine taking a trip along the integral curve generated by this Lie bracket, which will bring me here, and I will find that the metric form will not change. So from that I can conclude that along integral curves of Lie bracket of 2 killing vectors, the metric is also invariant, form invariant. So like this, you can generate killing vectors very quickly. If you have 2, you can generate the third, and you can take the killing vector of the Lie bracket of the third one with respect to the first 2 and generate even more. And this process can continue, can be continued. Now you can ask how many killing vectors for a given spacetime can we write down? What is the maximum number of possible killing vectors? And maximum number of killing vectors possible for a Riemannian manifold of dimension n is given by this number. I won't supply the proof of this, but you can look at O'Neill's book. Also, Weinberg's book, I think, has a proof of this. It says that if you have an n-dimensional manifold, then the maximum number of killing vectors the spacetime can have is given by n times n plus 1 over 2. Okay, this is the maximum possible. So these are highly symmetric spacetimes. In fact, these are called maximally symmetric spacetimes. And I'll cite a few examples. Any student, serious student of general relativity should be familiar with the common maximally symmetric spacetimes, which are, if you have purely Riemannian manifold, that is no time, only spatial directions are there, then the maximally symmetric spaces are only in 3 types, which are the Euclidean hyperspace, the n-dimensional sphere, and Hn is the n-dimensional hyperbolic space, which is the negative curvature space. Although we have not introduced curvature, I will still say that the first one, that is n-dimensional Euclidean hyperspace, has 0 curvature. N-dimensional sphere, Sn, has positive definite curvature, and n-dimensional hyperbolic space has negative curvature. So these are the 3 maximally symmetric spaces for Euclidean signature. And for Lorentzian signature, that is, if you have one time and rest of them space, the maximally symmetric spaces are Minkowski space, again, which will have zero curvature, n-dimensional de Sitter space, which has constant positive curvature, and finally, n-dimensional anti-de Sitter space, which has constant negative curvature. Okay, please wait for the next couple of lectures where I introduce the notion of Riemann curvature, and then we will talk about maximally symmetric spaces again. But here, I'm just going to mention that the number of maximally symmetric spaces is very few, and they are these geometries. Okay, I hope that will conclude the part of the discussion, which is focused on solvability of the geodesic equation and how you can do that using conserved charges, for which you need to determine the Killing vectors. And this is a direct method would be to solve the Killing vector equation themselves before you solve the geodesic equation. And sometimes, if you're lucky, you can figure out the Killing vector by simple inspection, which is what I described. And then if you have a few of them, you can start taking Lie brackets of all those and generate more Killing